And today I have to thank Ronan for this kind of invitation and for this very difficult task, because speaking about surgical data science after an hour talk from Dan, it's very, very challenging. But I like challenges, and this topic is very close to my heart because I'm a surgeon in training at Rome Gemelli, where I direct a lab working on the topic. And I'm a clinical research advisor on AI and computer science at IHU Strasbourg, the Institute of Image-Guided Surgery, the university part of IRCAD, let's say, where I did my PhD on the topic. This was back in 2017. And many back then said that I was losing my mind to join a computer science team. 40 computer scientists that never really spoke with a clinician before. And to go back to some previous questions, since I think I'm thinking on how to pivot my talk, because basically Dan covered 80% of it, much better than I can do, probably. But to go back to some previous questions, back then I think the barrier to entry was much higher, because I spent more or less 1.5 years not understanding what my supervisor was telling me, computer scientist Nicolas Padois, and he was not understanding what I wanted to do. So we needed to learn a common language. I think right now this field is moving so quickly, and it's also leveraging down a bit. So we're getting more familiar. There's still much to do, but these tools are getting democratized. It's easier to enter in the space, also thanks to this kind of events. Well, I'll start on the topic then. Surgical data science. I have 20 minutes. How do you move this? I'll start with context and need. And I think it's very important to do so, to always ground our work into our mission, so to improve surgery. Surgery looks much more like this today. And this is very different from what it used to be. The surgeon is no longer necessarily on top of the patient, but there are some digital machines, and these have been very broad on purpose, between patients and the delivery of care, which has made surgery much more efficient than it used to be, effective, to the point that today surgery is a major component of healthcare system, and it's not always been the case, both in terms of number and in terms of cost. But I'll go straight to the point. I think we live in a paradox, the black box paradox, which is not only AI, but I would argue here, and probably this is a little bit provocative, it's surgery, because it's the bit of healthcare that we know the less. It's very difficult to tap into surgical data, information in operating rooms. Operating rooms today, and they've always been, are much like changing rooms. What happens there stays there, which fundamentally limits our ability to study what happens and to improve it. We historically have done that mostly indirectly, looking at patient presentation, outcomes, and correlating the two. Today, especially with minimal invasive surgery, but in general with the growing integration of digital technology in the operating room, we have a huge opportunity to model this natively digital information in order to improve care. And what we can improve is for sure training, because we never have to forget that half of the world population does not have access to surgery due to a lack of trained workforce. Not only surgeons, but surgical teams. It takes an average of 10 years and very large investments to train these people. And if we could model information and move out of the operating room at least some part of this training, we could probably make it much more efficient. But even where surgery is available, surgery is at least suboptimal. There's 3 million post-operative deaths per year, and this translates to up to 29 billion cost in the United States every year. And the opportunity is that in the last few years, led by the World Health Organization, lots of studies have found that about 40% of these intraoperative adverse events can be prevented, are due to human errors that can be prevented And we believe that modeling information can help with that. But what do I mean with modeling information? We believe in AI-enhanced surgical quality assurance. And in these slides, I'll try to exemplify that. First, we need a piece of data. And in our view, an ideal piece of data are videos and images for a number of reasons. First, surgeons use this sense to guide their procedure. They always have been, and especially minimal invasive surgery, where vision complements the lack of haptic and other senses. But also because vision is quite democratic, because I don't need to tap into a platform, a company, and it's very replicable. And it's also quite scalable because, of course, I can sense directly at the surgical field level with endoscopic vision, and that's the easiest. But it's not difficult to imagine to capture also open surgery, and groups have been doing that for some years now, and also at the level of the ambient. So cameras cost a few euros. Most operating rooms today have ceiling room cameras, and this has been leveraged for studying OR teams' interactions, where probably there's a lot to improve. Then we need to make sense of this unstructured piece of data, because videos are complex data. This is what calls for two things: domain expertise, which is the most important thing. So surgeons that make sense of these videos in order to understand pitfalls and solutions for that. And this is happening at scale in the last 10 years. Probably the first groundbreaking work on that was Wickmeyer, Superside, New England Journal of Medicine in 2013. But this now is highly replicated across many procedures, so showing that intraoperative events affect outcomes and how to improve that. But this hasn't scaled yet to clinical practices because it's just unfeasible to have surgeons reviewing hours of procedures, and it's also not real time. And this is what deep learning is particularly good at, replicating some expert assessment and scaling it in time to provide intraoperative assistance, so improving the care we deliver to the patient we have at the end of that given time, but also in quantity, so to build the information, the knowledge we need to optimize care. And in our vision, that will enable what we call a surgical control tower. So an app that is there to monitor activities, to have a bird view on operating room activities, anticipate possible adverse event like an aviation control travel. The control tower informs whether two trajectories will collide and intervene to prevent that. So this was the bit about context and needs. Please interrupt me at any point. As Ronan said, the coolest thing of today's discussion probably. I will now speak about a little bit of the technology that is powering that. A good part of it is deep learning. So Dan said very well that that's not all, it's not alone, but deep learning is still what has powered most of the shift forwards of these last few years. Because these techniques are very powerful when there are complex pieces of data, like video or text, with nonlinear correlations. Very simply put, these deep learnings, the deep neural networks, are a collection of neurons that were inspired by biological neural networks. Actually, the first works were from neurobiologists back in the 50s of last century that were trying to model how neurons work. And again, it's an oversimplification. They learn with experience as we learn, and experience is data. In the most widespread paradigm, supervised learning, we have a piece of data that we feed to a function, This, at the beginning, is a naive function. So it's a function that does not know how to solve a given task. And this function gives an output. At the beginning, we expect that output to be random. This output is compared with what we call ground truth, so the reality. This is usually annotated by surgeons in our case, to compute what we call a loss, an error. This error is the information, the signal we need to retropropagate and tune the millions of parameters of these functions in order to optimize its output and hopefully get right answers. So again, forgive this oversimplification, but I think it's good to give an idea of what the major paradigms are. And these techniques have evolved hugely in the last 15 years. And so are their translation, actually translation is the wrong word, their more surgical application. So if the KAMA lab, the lab where I come from, was publishing back in 2017, and this got quite some visibility, system to understand the workflows of procedures. So how procedures develop in steps. As Dan said, that's also how surgeon in training like me learn the first steps. Understand what tools was present in the scene, estimating remaining surgical duration. Today, the state of the art is advancing a lot. Today, we are able to model what Nasir Nawab, the godfather of this field, likes to call the language of surgery. So tool-tissue interaction at a very fine-grained level. This is the work of Cinedu Nwoye from the lab, basically model surgical activities defining what he calls triplets, composed of effector, the tool, the action, a verb, and the target, the anatomy. And what you see when it's in green, the model is basically matching the ground truth, the reality. And when it's in red, there are inaccuracies. So this is a little bit about, again, very high-level view of the technology that is powering that. I'll give an example of its application to surgery. Dan, again, spoke about it already quite vastly. So I'll try to avoid overlapping. So here the audience is mostly surgeons, but not only, so probably it's good to remind that lap chole is the most performed abdominal surgical procedure worldwide. And as you can see in the video here, the surgeon has no hesitation at all in clipping and cutting what he or she believes to be the cystic duct first, artery then, and then finds unexpected anatomy and realizes that that was a major bile duct injury, so complete transection of the biliary tree. So this problem has been well known for more than 30 years. And back in 1995, a surgeon called Stephen Strasbourg basically translated to minimal invasive surgery common knowledge in open surgery. So identifying some landmarks that makes you sure that what you have identified as the cystic duct is the cystic duct. This is a concept derived from hunting, where you need to be sure about what you're shooting at, secure target identification, and so you need to recognize some key elements of it. It's called the critical view of safety, and it is now recommended by all guidelines on safe chole as a fundamental step to prevent bile duct injury. So once you get that view, you know that you are clipping the cystic duct and not the common bile duct. And it's still a very relevant problem because lap chole is common, even though the incidence of bile duct injury is low, in between 0.5 and 1.5%, according to the only registry data that we have so far. It's still 3 times more common than in open surgery. I was very impressed by a comment of Santiago Organ CMO of Stryker and director of the Center for Future of Surgery in San Diego, saying we are lying to patients when we tell them that lap chole is the best possible procedure they can get, because numbers show that it's still 3 times more common to get a bile duct injury. And high number, even though there is low incidence, means that according to a SAGES survey, so probably the society that has done the most for safe chole, 1 in 2 surgeons, so every other surgeon, experiences a bile duct injury in their life, translating in 3 times the mortality risk at 1 year for patient, $1 billion per year in the United States, and medical legal consequences. We've been applying surgical data science to this problem. So thanks to Dan, I don't have to explain all the different steps. I'll go very quick on that. First, we looked at how to convince surgeons to implement more often the critical view of safety. So data helped us a lot with that. 1 year of data collection and review in double blind, 16% CVS implementation. Simple cognitive aid that we call 5-second rule. We just went to the staff department, to the staff meeting, and asked them to stop before clipping for 5 seconds. The surgeon has to recall the 3 criteria defining the CVS to the assistant. And that simple act of recalling the right information at the right time translated into a jump of 70% of CVS implementation in the first month, and that plateaued at 44 over the following year. These are 343 procedures. And that to me was probably the easiest research we've done, and the most impactful, I believe. Then, if you know you need to implement, it's good to have some tool that guides you towards this implementation. That's the work that Dan explained already, GoNoGoNet, led by Amin Madani. We worked on automatically assessing this critical view of safety, both to guide surgeons towards achieving it through semantic segmentation of relevant anatomy, but also to give an automated intraoperative safety check. And imagine that in a pipeline with the 5-second rule timeout, you're not only recalling that information, but you're getting a second opinion on that. Then we want to document whether this KPI improves or not. And we want to make it more efficient. So we built EndoDigest. Simply put, you input a video and it outputs a 2 minutes and 30 seconds long video clip that in 91% of the cases is effective in documenting this critical step of the procedure. And here I like to reconnect with the discussion on metrics that was done before. So if we look at that application from a computer science standpoint, we were measuring how well does the system identify the time of the cystic activation with mean average error in seconds. That does not tell us very much. So what we did is we did a user study. So I think optimizing matching for the end task that you want to build is very important, but there's also user study that have to be done to see how these impact practice. So we gave to one surgeon the full videos, to another surgeon the AI generated video clips of 2 minutes and 30, and in 91% of the cases they could evaluate the same thing. So this led, this was a lot of work done with the wider community, led to a lot of publication, a successful PhD, but the reason why we start and we spend so many hours on all that work is to go into clinic. And this is what we have tried to do back in 2020 with a collaboration with NVIDIA. So what we did is to take on a challenge. We took 5 models that might serve different stakeholders in operating room and that we know the technical performance about. We pulled them together to output something like this: face detection, anatomy segmentation, continuous assessment of the critical view of safety, and tool tracking. We worked a lot with NVIDIA to optimize this collection of deep learning system on their Clara AGX. Back then was a developer kit, now it has evolved a lot. And basically we de-risked that in the experimental operating rooms of IHU Strasbourg. And basically, as you can see today, we got to the point, as you can see in the slide, we got to the point where there was no lag in the basically AI augmented video. So, and then our next challenge was, how do we demonstrate this to the wider public that is very skeptical that this kind of assistance can be brought in DOR in real time without waiting 5 years or plus for regulatory approvals and all of that. And the idea was to capture the video, avoid analyzing it, avoid feeding it back to the operating surgeon. So you don't intervene, we didn't intervene on the delivery of care. The surgeon was doing a normal laparoscopic cholecystectomy, but we broadcast the AI augmented video to the World Congress of Endoscopic Surgery and to the Palazzini in Rome, 25th of November 2021. About 70,000 surgeons viewed the broadcast. And for us, I mean, I was commenting that with my mentor Bernardo Alemagna, and for us that was very emotional because finally we saw that these things were translating in practice, even though it was not still acting on the delivery of care. That was for us a technical proof of concept, and I like to stress that because we don't expect this to be used that way in operating groups. This would actually disturb, would not help. Everything is so explicit because we wanted to show what the machine was assessing. What we are now working on a lot with human factors, expert designers, ergonomics, is to understand what information to give to whom and when. Nothing less, nothing more. And where are we? We are very far from where we want to get. These two slides summarize a little bit the commercial space of AI in surgery, of vision in AI, computer vision in surgery. There are some companies that have the merit to bring this for post-operative intelligence and that have started to implement deep learning in their systems. Even though this is, technically speaking, not the state of the art, I expect that to be because it takes a long time to put that in a commercial product. But what I'm even more interested about is having AI approved as a medical device. Because the previous platforms are post-operative. These are not medical devices. So if these are not medical devices, and this is important to stress, they don't have a clinical intended use. So they're not meant to improve the care you deliver. If you have a clinical intended use, it's a medical device. And FDA database, which is public, shows that there's only 2 approvals for AI, ML enabled medical devices in surgery. One was from Gauss Surgical, later acquired by Stryker. And I'm very curious to ask you whether this is on the market because I'm not understanding whether it is. And the other one is the accessory AI built on the Transenterix robot, Ascensus, recently bought by Custos. But that's it. There's no other AI system in surgery approved today. Why is that? Expectations are high. Surgeons expect this to be translated. And surgeons are willing to use it, especially after training. And I'll get to that later, as Dan was saying again. Why it's not implemented yet? We asked about 700 surgeons across 90 plus countries in 2 surveys we did in 2021 and 2024 that we are about to publish. And we are releasing the data set for the community to analyze as well. First challenge is infrastructure. There was a question about that earlier in the room. And I think this is being solved by big MedTechs. Everyone, and I don't have relation with any of these, are digitalizing operating rooms. are building the iPhones, are building the infrastructure we need to deploy this technology in operating rooms with different strategies. And it's a very exciting time because it's super interesting to see how different companies are thinking and solving that. Second big barrier, and this is, I think, very important to surgeons, is the lack of AI tools of surgical value. I think there's a lot we can learn from AI-assisted colonoscopy. AI-assisted colonoscopy is probably the biggest success of AI and the quickest success of AI in medicine today, much bigger than radiology, in my opinion. And the reason why I believe they have this big success is because they identified a very well-defined KPI, a very well-defined endpoint to prove. So simply put, adenoma detection rate correlates with interval cancer and colorectal cancer mortality. It is highly variable across practices, and we have a ton of data to train an AI for that. They built it, and I'm proud to say that the first de novo was an Italian story, Cosmo, that is now distributed by Medtronic. And they translated very quickly. Approval in 2018. In a few years, it's the technology that has the most evidence, the most randomized controlled trial in medicine. And recent meta-analysis, plus 18% of adenoma detection rate across this randomized controlled trial. Huge commercial success. My timeline stops at 2022. It's not even all the players that have commercial system. I think we need to do something like that in surgery, but it's much more difficult because our KPIs are much more unknown. I have to thank Bernard D'Allemagne that the first week I was in Strasbourg told me focus on clinical biosafety because it's one of the few KPIs we know. Not everyone agrees, but all guidelines suggest it. So it's a good place to start. And I believe this will explode in the next years because there is a big push from societies to start to understand, break the surgical black box paradox and identify more KPIs through video-based assessment. Finally, and this is my last slide, I promise, what Dan was saying, so the cultural bottleneck related to the hype and skepticism on AI. The explainability problem is a big one, but it's not the major one, I think, for a scientific reason. We give paracetamol and we don't really know how paracetamol works. So if, as Ronan was saying, we have a trial that shows that paracetamol solves your headache, you take it. I would argue that here the problem is more complex because not knowing how the system works, it's very difficult to identify the good range of uses. So in a mechanical system, we know it's calibrated in a certain range and doesn't work outside of this range, a scale. In AI, as of now, the only way we can do that is testing at scale. Unpractical. We will never test every edge case. Surgical AI is a long tail problem. But there are technical solutions that are appearing. For instance, I really like the research direction of auto-distribution detection. So a model that tells you when it doesn't know because a certain piece of data is not well represented in this training set. And the other big problem that I believe is still widely understudied is how we interact with this system. Again, Dan, I've cited you 100 times, mentioned about this. You're more likely to trust a system when you know why it's giving you certain prediction. And I think this radiology paper shows the concept very well. Even expert radiologists, when suggested the wrong diagnosis by an AI system, tend to give a wrong diagnosis. And without the AI system, they give a good one. We have all experienced taking the wrong road, the wrong turn, just because we were following the GPS, even though we knew the right street. And for that to be solved, I think we need education. We're doing that thanks to the support of the European the European Association of Endoscopic Surgery. And this year, we will organize the 3rd masterclass, so a full day dedicated to surgeons that want to know more about this. And in Strasbourg, we organized the Surgical Data Science Summer School. So if the masterclass is for surgeons that want to understand what's going on, The summer school is for surgeons and computer scientists that want to build this technology. 5 days, 8 to midnight, 50%, Andrew was there, this is why he's laughing. 50% computer science classes, 50% surgical classes, and the scope is really to learn a common language between the two communities. I'll stop there. Thank you very much. Hopefully there's some discussion.